Hi 501ers. Uh, in this video we will be talking about contact stresses, and as we talked in class, one of the goals of this video is to give you experience while you're in school about ways to continue lifelong learning. So contact stresses are really important because they can be very damaging and very high. I've actually done some work with contact stresses in tires, in automobile tires, where we looked a lot about the stresses that develop in the tire and areas over which those stresses develop. There's also some interesting analysis that can be done with contact stresses in sports equipment. For example, how can you maximize a sports device to input as much energy to the ball as possible? How can I design a bat or a tennis racket so that I get more power or more energy out of that bat or racket? Gears, there's a ton of analysis that is done and being done on the stresses that interact on gear teeth, and are there certain shapes of gear teeth or materials or designs that could be used that would minimize the contact stresses? You can see in this example, in this picture, that here we have really high contact stresses where the two gear teeth are meeting each other. And down here we can see that this gear tooth should act somewhat like a cantilever beam, and we see stresses here and here that are also high, but not nearly as high and pronounced as the contact stresses that occur up in the tooth. Another one that's very interesting is contact between an infinitely flat surface like a railroad, not a tie, but the railroad rail, and then the train wheel. Very high stresses develop between these two members because they're both high strength, not a lot of deformation. And if you walk along a railroad track, you can often see pitting and corrosion that has occurred on the surface of the rail. So lots of cool things with contact stresses. Again, they can be very damaging, and it's important that we understand how to design to minimize those, and certainly how we can analyze those. Heinrich Hertz, back around 1885, did a lot of research in this area. And this is the same hertz that we talk about when we talk about vibration, and the units of frequency, where we give those in units of cycles per second, or hertz. This is the same guy. So with that, we'll go ahead and jump into the development of some of the expressions for contact stresses. In contact loading, what we're looking at is two bodies that are forced together, and they contact each other over a relatively small area. And what we want to do is develop an expression between the applied load P and the stresses that develop in that area. And we're going to follow chapter 17 of the Baresi textbook very closely here. He does a great job with this chapter, and so if you have questions or need more detail, certainly reference chapter 17 of your textbook. One of the first things that we want to talk about is the nomenclature, and it's a little bit crazy in this chapter because there's lots of different terms that we'll use and talk about. And so I've kind of built some summary tables to help us remember what these terms are. But if we look at two bodies, like shown here, that are together and being pushed on, we have definitions of the radii. And for one body, we call this small radius right here R1, and this major radius R2, and you can see that we actually use some prime values. So maybe I can grab this and blow it up a little bit so that you can see it. But R1 is this minor radius, R1 prime is this larger radius, and then when we go to our second body, R2 prime again is the large radius, R2 is the smaller radius. And so make sure you keep those definitions straight. Some more definitions that can help us are shown on this next page. But before we jump to those, let's look at what the values of R can be. If you have two bodies that are just rolling on top of each other, as shown here, you would have a positive R1 and a positive R2. If you had a body that was rolling on a flat surface, such as a railroad tire on a railroad rail, R2 would be in infinity, and R1 would be the value of the wheel. You can also have negative values. For example, if you had a sphere or a cylinder rolling on the inside of another cylinder or sphere, the R2 would actually be a negative value. Now if we look at some of the definitions of the axes, I'm going to blow this picture up a little bit so we can see it a little bit better. But here we have one member on an angle and one member located vertically. And when we look at these, the U1 is the longitudinal or long axis for the first member, and V1 is the short cross axis for that member, and then U2 is the long axis for the second member, and V2 is the short axis for the second member. Now, when these two members are pressed together, there's a contact ellipse that develops, and we will have an elliptical contact region between these two members. And this elliptical contact region has dimensions or a coordinate system of x and y. And this x and y coordinate system does not necessarily correspond to U1 or U2. We can write the equation of this contact ellipse as x squared over a squared plus y squared over b squared equals 1, where a and b here are the semi-major and semi-minor axes of the ellipse. And we will refer to those and use this equation later on in the development of the expressions for the stress. The angle alpha here is the angle between the two contacting bodies. So lots of terms here that it's important that we are familiar with and can reference and respond to. So you'll often want to look back at these notes down here and this picture if you get confused about some of the nomenclature. In contact stresses, we're going to use the coordinate system that was shown back on this previous page, where we have x and y in the plane, and given this coordinate system, positive z would be coming out of the page. So when we look at the z stresses, or the stresses along the z-axis, we would be looking at the stresses that go through the two contacting bodies. So the stresses on a stress element along the z-axis are shown down here in this figure A. And so this is a little chunk of one of the bodies, a differential element, along the z-axis that goes right through the middle of the contact stress ellipse. And it's important to note here that there are no shear stresses as long as the element is on the z-axis. So when the element is on the z-axis, the sigma zz, sigma yy, and sigma xx are the principal stresses for those positions. Now, shear stress does exist on other planes, and we can compute what that shear stress is by taking the difference between sigma zz and sigma yy and dividing by 2, or sigma zz and sigma xx dividing by 2, whichever value is the greatest would be the maximum shear. And those would occur on these different planes, but not on the x, y, and z planes as shown here. It's also important to note that these three principal stresses are all in compression. And so due to the contact loading, the three principal stresses will be compressive stresses. If we look at a stress element off axis, we still have a negative sigma xx, yy, and zz, but now we have these shear stresses that also develop in the element on these planes when we're off the z-axis. So in summary, here's a bunch of nomenclature that you need to make sure you review and are familiar with. P is simply the applied load. E1 and E2 are the modulus of elasticities of the members. Nu1, Nu2 are the Poisson's ratio. And it's really easy to get these Poisson ratio values confused with the V direction that was shown back here as the short coordinate direction in these bodies. But when you understand the equations, it's clear as to which one should be used. The A and B lowercase are the semi-major and minor axes, and the semi simply means that you take half of that value. So R1 and R1 prime we talked about. Here's our U's and V's, and these are the V's you want to keep distinct from the Poisson's ratio Nu's. Alpha is the angle between the bodies, the principal stresses, and the shear stresses. And now we're going to introduce a couple of geometry terms that will help us in the stress analysis. And these are K equals B over A, where the B over A are the semi-major and minor axes of the contact ellipse. And then K prime is 1 minus K squared quantity square rooted. And you will see where these expressions come in later in development of some of the equations. The equations for the stresses in a contact situation are fairly difficult to derive. So we will just go over a kind of a quick overview of how they are derived because the derivation is certainly not the focus in this class. I want to give you enough of a background so you see where they come from and what's involved with coming up with them. But our focus will be on using the results appropriately. The basic idea in developing the equations for the stresses is if you take two bodies as shown here and you take a point Q1 and Q2 that are on those bodies, they would initially be separated by a distance d, where z1 is the distance from the tangent plane here to Q1, and z2 is the distance from the tangent plane to Q2. Both of these would be given positive numbers because the distances are positive if you're moving into the body. And so what we then do is apply a load P. And as we apply a load P, you can see where this top disc flattens out some, and we get a contact area here that grows. And Q1 and Q2 become in contact, or certainly come closer to being in contact. And if you take this distance d for points q1 and q2 around the whole body, around in this direction like this, you can write an expression for d as d equals ax squared plus by squared, where x and y are the coordinates around the z-axis, and a and b are coefficients that we need to now determine so that we can come up with an expression for d. This kind of shows d in more detail than on the previous page. Here we're showing that the origin of the xy coordinate system is the initial point of contact at the center of the contact ellipse, and the equation for the contact ellipse, as we remember, is this x squared over a squared plus y squared over b squared equals 1. Now this equation is different than the equation for d that we're talking about here. This d is given by ax squared plus by squared, and d is the distance between corresponding points on any two surfaces. So it's the distance here between q1 and q2, where this equation here is for the contact ellipse that's going to be generated when we press these two bodies together. So there's a difference between these two equations. It's important to keep them separated. Now, in order to determine expressions for A and B, we need to use the information that we know. And typically what you know in two impacting bodies or two connecting bodies are the radii and the geometry of the two bodies. So we want to solve for A and B in terms of radii of the connecting bodies. To solve for A and B, we're going to look at just one of the disks in the unloaded state. So here we're taking the center plane of the disk. Here's our tangent or our contact surface, and we're going to put points C and D at distance Z1 up above on the disk. And again, if we were to wrap this around the disk, we would get this ellipse looking geometry like this. So what we need to do is come here and get an expression for Z1. And to do that, we're going to define some geometry. If this angle right here from the center of the disk to point D, which is our arbitrary point at Z1, so the angle from the z-axis out to that line is beta, then if we come down here and we come out the distance u1 and up to D, this angle can be shown to be beta over 2. And the tangent of beta over 2 would be equal to the opposite side, which would be z1, over the adjacent side, which would be u1. So from the figure above, we have the tangent of beta over 2 equals z1 over u1. And this solving for z1 leads us to u1 tangent of beta over 2. And if beta is small, such that the tangent of beta is approximately beta, then we can write z1 as u1 beta over 2. Then we can look at the triangle HKD. So the triangle HKD comes from H, K, and D. If we look at this triangle here, we can write that the tangent of beta is u1 over r1 prime minus z1. And if we assume that r1 is much bigger than z1, then we can let the tangent of beta equal beta, and beta is equal to u1 over r1 prime. And now we're going to substitute this in to our expression for z1, and we can see that z1 would be equal to u1 beta over 2, which can be written as u1 squared over 2 r1 prime. Now if we look at the triangle HKF, so we're going to come down here and come to HKF, and so this is looking into the page for the triangle. We can write a similar expression where we can say we can solve for Z1 in terms of V1 and get V1 squared over 2R1. So now based on these two definitions of Z1, one in the U1 direction and one in the V1 direction, an equation for the distance Z for any point on the surface can be determined because we have two unknowns, A and B, and we're trying to determine what those coefficients are, and we now have two equations to do that. So we can write Z1 as U1 squared over 2R1 prime plus V1 squared over 2R1. Now assuming that our Z1 assumption is valid, we can show that by letting V1 go to 0 and we get our result. We can let U1 go to 0 and we get the result that's expected. So we kind of validate this equation doing these boundary conditions. And going through a real similar analysis for Z2, we can show that Z2 is given by this expression here. So now coming back to our expression for D, we can write D is equal to Z1 plus Z2, and we can fill in all of these terms. And now what we need to do is get expressions for U1, V1, U2, V2 in terms of our X and Y coordinates. And this is done by simple coordinate transformations. We know the angle alpha, and so we can get expressions for U2 and V2 using alpha and U1, V1 as shown by these equations here. Then we can substitute those into our expression for D and get this result. And now we need to do another transformation where we transform from U1, V1 to X and Y, and we'll use this transformation and the angle lambda, where this angle lambda is shown in this picture up here. And doing that, we can get an expression for D then, where A and B are given by this big long expression right here. This is the expression for A in this equation. If we want to compute B, the only difference between B is this is a plus sign for B. So we're going to see how we use this expression for D in a little bit, but the main takeaway that I want you to have is that A and B come from simple geometry analysis of our two undeformed bodies back using this picture here that's 17.3a in your textbook. Now there's a couple special cases that you want to be aware of that occur commonly in analysis and design. And this first special case is when the major axis of the contact ellipse is along the x-axis. So here's my contact ellipse between the two bodies, and it's shown to be along the x-axis here. So in this case, my alpha equals 0, and my b over a would be greater than 1. This condition is often considered or called the direction of rolling, or rolling direction. And in this example, we would have an R1 and an R2, say, equal to 10, and an R1 prime and an R2 prime equal to 5, and that would give us a condition like this. Now another condition is when the minor axis of the contact ellipse is along the x-axis. So here my contact ellipse is rotated 90 degrees. In this case, my alpha is still 0, but my b over a now is less than 1. And this would be a situation where my R1 was infinite, R1 prime 440 for example, R2 330, and R2 prime infinite. So these are just some special conditions that you might come across in some of the problems that we'll be working later on. What we want to do now is talk a little bit about the solution for D that we just came up with. So what we're going to do in this picture right here is we're going to let these two bodies be in contact with each other, and we're going to push on them with load P. Now, because these bodies are elastic, as they compress, they're going to stretch out and deform and flatten out. And so Q1 moves down a distance delta 1, which would be this full distance if it was rigid. But since it's elastic, it really only moves down delta 1 minus this W1. And that would be the distance that point Q1 actually moves down, because it's an elastic body and not a rigid body. Back here, when we derived the expressions for A and B, using this analysis, we assumed rigid bodies. But now we're letting them deform, and when we do that, we realize that delta 1 is not exactly what Q1 moves down, but Q1 moves down delta 1 minus W1. And the same thing here with Q2. So when we come down here and write this, what we're going to do is we're going to say D now then is equal to delta 1 minus W1 plus delta 2 minus W2. And rearranging this, we can say D is equal to delta minus W1 plus W2, where delta is the sum of delta 1 and delta 2. So now we can say that D is the distance Z1 plus Z2 like we've always used. It's given by this expression right here. And now we can write that as delta minus W1 plus W2. And so rearranging this, we can solve for W1 minus W2 as equal to delta minus AX squared plus BY squared. And what we want to do now is solve for W1 and W2. It's important to note that this equation was developed solely on geometry. Only geometry was used to come up with this expression. And we want to solve for W1 and W2 now, and that's not a trivial thing to do. This is kind of where Hertz came in. And I don't know how in the world he did this, but he noted that this equation has the same form as the Newtonian potential equation for the attraction of a homogeneous mass M in the shape of an ellipsoid on a unit of mass concentrated at point P some distance from the ellipsoid. Wow, I can barely even understand what's being said there. However, Hertz realized this and knew that he could come up with a solution using elliptic integrals. And so if we come down here, the solution to this problem up here can be given in terms of elliptic integrals, and these are the definitions of the elliptic integrals that we will use. And if you remember, we introduced a K prime value early on, defined what that was. That's going to come into play here. So when we say f of these terms in these brackets, this represents an elliptic integral. H represents a slightly different elliptic integral. K and E also represent different elliptic integrals. And these are defined here. We're probably not going to use these definitions too much because there's lookup tables and other ways to compute these integrals that are a little bit easier for us. But our solutions for the stresses will be based on these expressions here. So the following expressions can be used to compute the principal stresses. So we have sigma x, y, and z, and this is given by m, omega, nu, omega prime, d over delta. So let's make sure we understand what these terms are. The M is given by this expression here, where we have 2k, and k is the ratio, and k prime, and then the elliptical integral of k prime. So this is M. Then we have omega, and the omegas come from these expressions down here. So omega x is given by this equation, where f and h are elliptic integrals. These equations are given on page 598 of your textbook, and these equations are given as these equation numbers here. This new in here is Poisson's ratio, and it takes on the value of the body that you're looking at, and then omega x prime is given by this equation, which has elliptic integrals in it. And then we have b over delta, and we will see where we will come up with an expression for delta here. This b is the area of the dimension of our contact ellipse, and we'll get an expression for delta here in just a minute. To finish with some of the equations on the previous page, we can compute the ratio of b over a using this equation here, where again e and k are elliptic integrals. Then b, the semi-minor axis of the contact area, is given by this expression here. So the stresses are functions of capital A and B, K and K prime, Poisson's ratio, modulus of elasticity, semi-major axis of the contact ellipse, and Z, which is the distance along the Z-axis to the point of interest where we're wanting to compute the stresses. So these expressions here are very detailed. There's a lot of computation in them, but we'll see that it's really not too difficult once we get the process down. This will be the method for computing the contact stresses. The first step to compute the contact stresses is to determine the values of A and B, and we come up with the equations to do that, and then we get the ratio of B over A. Then we can compute K and K prime, and with these values we can compute the terms in the brackets of the stress equations shown down here. These terms in these brackets, we can compute those. Now, a couple things to remember about this is sigma ZZ will always be the largest principal stress, and it will occur on the contact surface. Sigma ZZ and sigma YY and sigma XX are largest at the point of contact. So right on the surface where the two bodies meet. These three stresses are the principal stresses. If we have two cylinders that have their longitudinal axes perpendicular to each other, it gives us a contact point. B over A would be equal to 1. Now if the two cylinders have their longitudinal axes parallel, this gives us a line contact along the axis, and B over A would be equal to infinity. So there's some cases where we can actually just know what B over A is. And the equations for the principal stresses are given by these expressions here. The terms of in the brackets of these equations can be computed if we know Poisson's ratio, A, B, K, and K prime. Now, kind of an interesting thing here to note, though, is that the bracketed terms are not strong functions of the elastic constants or the load E. What that means, they're not strong functions of the material properties or the loading. So we can often assume a value of Poisson's ratio, and then we can put the bracketed terms in a table or a graph, and based on our B over delta term, we can compute the stresses. So this is a really cool thing. We're going to kind of bypass computing the guts of these brackets just because we know that they're not strong functions of the material properties, Poisson's ratio, and because we know that they're not functions of P. And so we can come down here and table this thing, make tables for these quantities, just assuming Poisson's ratio is equal to 0.25. Now, if you have a vastly different Poisson's ratio, you may want to go in and compute these, but likely that won't occur. So now we can use a table. We'll use figure 17.4 on the next page to look at some of the stresses that we get under these conditions. But to continue on with the method for computing the contact stresses, after we've done this, we'll use the specific values of Poisson's ratio for the contacting bodies to compute B over delta. And then the X, Y, and Z axes are the principal axes, and there's no shear on these in these directions. However, at angles to these axes, there is shear. And so the shear stress on the contact surface is 0 in the X, Y, Z directions, but there's shear stress in the other directions if we rotate the axes. And then we'll use this figure 17.4 to identify and learn about the principal stresses. In this figure down here, the vertical axis are the values of the principal stresses. So this top curve is sigma ZZ, this curve here is sigma YY, and this curve here is sigma XX. Okay, and so just looking at those, you can see that various amplitudes change. This is as B over delta gets bigger, goes in this direction. And then my x-axis down here is distance from the contact surface. So these are values of kz over b. So as we get further from the contact surface, we see that the stresses significantly decay. This was given for this set of K and B over A ratio. Now what we note here is that sigma ZZ, like we talked about, is always the largest principal stress, and sigma XX and sigma YY actually change places. So right at a distance of 0 from the contact surface, sigma YY is going to be larger than sigma XX. But then as we cross through about 0.22 or 0.25 or so, these two stresses switch places. And that's important because we often want to look at the maximum shear stress. And the maximum shear stress is given by the largest difference between sigma ZZ and either sigma XX or sigma YY. And so when we look at the shear stress, we can see that we get this type of a curve. And what's interesting about this curve is the maximum occurs at a distance from the contact surface and not on the contact surface. These normal stresses have a maximum at the contact surface, but our maximum shear occurs at a distance that is off the contact surface by this 0.43 type kz over b distance. And so that's a key takeaway from plotting these curves. This is where we will finish the discussion for this video lecture. When we meet on Monday, we can certainly talk about any questions that you have in more detail. Thanks for watching.